Hi, this video lecture is going to be starting chapter 2. We're going to be talking about Fourier's law in more detail. So Fourier's law is a rate equation that allows us to determine the conductive heat flux if we know the temperature distribution in a medium. So knowing the temperature distribution, you've also heard me refer to this as a temperature profile. It's basically just saying we know something about how temperature changes with space over some solid. So for example, if we had a little coordinate system here and we had x in this direction and y in this direction, we could plot, and I'll just put them here for a little more clarity, y and x. If we were to plot temperature and how that changed over x and y, we would produce a plot that looks like a topographical map, and we'd get something called what's called an isotherm. So an isotherm just means a line of constant temperature. So knowing how temperature changes in this two-dimensional system by having this topographical map where we might have these different lines and temperature is increasing in this direction, we could actually use that information to calculate the gradient and figure out how heat is flowing. And if you recall from previous lectures, heat is going to flow against the temperature gradient. So if we were to calculate the temperature gradient using this topographical map, our temperature gradient would be going this way, which means that our heat is going to flow against that gradient. So if temperature is increasing going toward the origin here, then heat is going to be going away from the origin, according to this form. So the negative sign is really important there, and that basically it has a really important mathematical meaning. It says that heat flows in the direction of decreasing temperature. So heat is going to flow downhill. If we have this topographical map and we're able to plot things out with increasing temperature represented by these lines, then our heat is going to flow downhill against the temperature gradient. This is also the way that you would determine what the thermal conductivity of a material is. You would just rearrange that equation. You would measure the heat flux and you'd measure the temperature gradient. And if you didn't know the thermal conductivity, you would solve and say, oh, heat's flowing really, really fast through this material, so it must have a high thermal conductivity. Of course, the people who do that would be much more scientific. So the direction of heat transfer is always perpendicular to the lines of constant temperature. So if you have an isotherm, let's say another line looked like this, well, heat would be flowing normal to that line or perpendicular in this direction up here, but it would be flowing the other way here because it's going perpendicular to those isotherm lines. And then you can also take this heat flux vector and break it down into different components. So here, at this particular point, our overall heat is flowing this way, but you could break that down into the x component and the y component. And we'll talk about this more, and hopefully it'll make more sense when we see this example. So if we were to take this form of Fourier's law and break it out into the different components using Cartesian coordinates, this is how this vector would look. We'd have this x component, where the heat flowing in the x direction is proportional to minus k times the derivative in the x direction, and then multiplied by this I unit vector, which is the unit vector that points just exactly in the x direction. And we'd have the same thing for y, which corresponds to the j unit vector, and z, which corresponds to the k unit vector. So again, this is some pretty serious looking calculus, but let's try and break this down into an example that might make a little bit more sense. So let's say that for whatever reason we have a solid and we're able to determine that its temperature profile looks like this. We figure out that temperature, and this is totally hypothetical, made up example just to illustrate this point, but let's say that temperature is equal to x squared plus y squared. And if we were to plot that, x squared plus y squared is the basic equation of a circle, or x squared plus y squared equals 0 is the basic equation of a circle. X squared plus y squared equals some constant over here is the real equation for a circle. So if our temperature had this equation, we would see when we plotted it on this topographical 2D surface plot, we would see these concentric circles being formed. So each one of these would represent a different level of temperature. So this interface between the dark blue and the lighter blue would correspond to 20 degrees. Similarly, here's 40 degrees, and here's 60, 80, 100, 120, and then 140 would be at the end of this gap out here somewhere. So let's say we have this solid and we're able to somehow determine that the temperature follows this spatial map. So how would we calculate how heat is flowing? So first of all, is heat going to be flowing in this system? So the answer there would be Yes, definitely, because there is a driving force present. We see that temperature here out in these corners of our grid system is going to be higher than the temperature here. So there will be this tendency for that heat to flow from this higher energy state represented by a higher temperature down to this lower energy state represented by the lower temperature. And if we were to plot these different heat flux lines all over, we would see that heat is pretty much converging everywhere. However, the temperature gradient is going to be higher out here because of the nature of our equation. So we're going to see a higher rate of heat transfer out here than we would, say, more toward the center of this guy. So we'd see a less heat flow toward the center and 0 in the middle because it's symmetrical and there would be no temperature gradient right at the middle. Okay, so how would we apply Fourier's law? Let's just pick a point and calculate these different heat flux components for that point. So I'm going to use the point, just arbitrary, x equals 4 and y equals 4. So what we would do is we would differentiate our temperature profile, and we would get that dt dx is equal to 2x. We just take the derivative of this equation with respect to x, and then conveniently dt dy is equal to 2y. So then we would plug in numbers. So we would get dt dx at this point 4 comma 4 is equal to 8, and we would get dt dy at that same point is also equal to 8. We would plug that in, we'd calculate our flux. So our flux in the x direction would be minus k times dt dx, and for this example and the other examples that are going to proceed, let's just use a thermal conductivity of 1 watt per meter per Kelvin. So we would get a q double prime in the x direction being minus k times our gradient, so that would be minus 8. Similarly for y, we would also have minus 8, and these would have units of watts per meter squared. So if we looked at this point, our gradient says our gradient is 8 in the I direction, 8 in the j direction. So if we looked at each of those components in terms of just the gradient, our x derivative has a magnitude of 8 and our y derivative has a magnitude of 8. And our composite gradient is going to have this other magnitude, which is going to be bigger than 8. So our gradient is pointing uphill, and that tells us, that is confirmed. The reason those are positive is because they are pointing in the direction of our coordinate system. So with increasing x, our temperature is going up. With increasing y, our temperature is going up. And so together, if you increase x and y when you're out in this region, then you have your temperature is also increasing. However, when we apply that negative sign from Fourier's law, we get that our flux lines are going in a different direction. So if we do flux here in black, we see that our flux in the x direction is negative, which means it's going against our coordinate system. If this is positive x direction, then our flux is going in the negative x direction because of that k, the minus sign in front of the k. Similarly in y, it's going against our coordinate system, and the composite is similar. So here we have our flux in the x direction, here we have our flux in the y direction, and here we have our composite flux vector going down from this point 4, 4 down, should be pointing straight toward the origin. And that, if we could also apply the Pythagorean theorem and get the total magnitude of our flux, and that comes out to be 8.3, which it would just be, it would be the square root of minus 8 squared plus minus 8 squared. We would get our total amount of flux is that amount. So this, it's very mathematical to this point. I'm trying to just illustrate how to do this. But this is actually going to be very useful for us because we have this temperature map, and we will now know how heat is flowing from from this point. We know it's flowing in this direction, so applying Fourier's law gives us both direction and magnitude of heat flow if we know the temperature profile. This is going to come in really handy when we're doing energy balances and we want to know how temperature is changing in a fluid, but in order to know how energy is being accumulated, you need to know the rates in and out. So we would apply Fourier's law when the appropriate rate in or out is done by conduction. So let's look at another point on here. Let's take the point x equals -6 and y equals 0. So that puts us right about here. So that point is -6, 0. So let's calculate. So our flux in the x direction is equal to minus k times dt dx. We're still going to use that thermal conductivity of 1. So that gives us minus, let's just do this in smaller steps. So minus, remember our derivative was 2 times x. So we're going to have 2 times -6. So when we do all the math and plug in that k equals 1, we get, that's a terrible looking 6. Okay, so we get -12, and then we negate that again, and we get 12. So our flux in the x direction is 12 watts per meter squared. Our flux in the y direction, so our flux here is minus k dt dy, which is equal to minus k. We just look at our equation times, so minus k times 2 times y, but y is 0. So we end up getting 0 watts per meter squared in the y direction. But let's just look at what that means. So in the x direction, we have, this is, so we have our gradient pointing this way, which means we're going to expect heat to flow from left to right. So heat is going to be flowing this way. Notice that there's no gradient in the y direction, so there's, and if you look at the symmetry here, there's no, this isn't either, it's neither increasing nor decreasing when you go in the y direction. It's just flat at this particular point. So our vector is only going to point in the x direction. We notice the, so that's where the 0 comes in. There's no y component of the gradient, there's no y component of the flux. Our x component, you notice, is a positive number, which means that heat is going to flow with our coordinate system. It's positive, so it's going to flow with x, and x, increasing x, is going from left to right, and because we're positive here, our heat is going to flow from left to right with a magnitude of 12 watts per meter squared. Keep this one in mind because we're going to do another example in a later video on radial systems. Okay, so this is a two-dimensional system. We've assumed that nothing is happening in the z direction, so the z direction would be coming toward you out of the screen or going into the screen. So z direction is in and out of the screen, and we're just assuming that temperature doesn't change at all in the z direction. So our derivative with respect to z, our derivative of temperature with respect to z would just be 0, and we just neglect it. There's no heat flowing because the temperature doesn't change. There's no driving force for heat transfer in the z direction, and this is a hypothetical example, but often we'll make those types of assumptions to make the math easier, and because we're engineers, we want to get good, use good data and solve problems where we can have some kind of actionable step to take from our analysis. Okay, let's look at another system. This one is a one-dimensional system. So we talked about if our z direction is in and out of the screen and we're assuming that temperature doesn't change, well, the same thing is happening in the x direction in this particular case. You notice that t as a function of y is equal to y squared. T is not a function of x in this particular example. So if we traverse this plot in the x direction, we see that there's no change in temperature. All of our isotherms are just these straight lines. So basically this becomes a one-dimensional system, and we don't have to worry about the x direction. So if we plotted this, if we plotted t with respect to y, we would expect just a quadratic here. So we could look at this in one dimension. We actually don't need this two-dimensional plot. But I wanted to put it on here just to help you get a sense for how to make the assumption that a system is one-dimensional or not, and what are the implications of that. So basically, if we're assuming that t only varies in the y direction, we're just neglecting what happens with x. But you can see you don't really get much more information from this plot in the x direction. So if we had a point on here, let's look at our same point, 4, 4. So we have x equals 4 and y equals 4. Well, when we take the derivative of temperature with respect to x, so if we look at this guy, what's the derivative of that with respect to x? It's 0. So that part just goes away. Same thing with z. There's no z showing up in our temperature profile or on our plot. Well, it's hard to plot it because it's going in and out of the screen, but that goes away too. So this form of Fourier's law is called a one-dimensional system. This is a 1D Cartesian system. So we can calculate the flux. We don't even have to worry about this x component here because that's going to be the same whether we're here or here. It doesn't really matter what x is in this case because temperature isn't varying in that direction. So we're just looking at y. So our flux in the y direction is going to be minus k times the derivative of temperature with respect to y. And if we're still using k is equal to 1 watt per meter per Kelvin, then we end up with our flux in the y direction at this particular point is going to be minus k, and then our derivative is 2 times y. And if we plug in our y coordinate of 4 there, then we get minus 8 watts per meter squared. So that's telling us it's going against our coordinate system. Heat is flowing downhill from here. So it's because it's going, temperature is increasing, and our gradient shows that in this direction. So heat flows against that gradient. It flows downhill from hot to cold. And looking at the form of this, the bigger y got, because our dt dy is this simple function of y. That means the bigger y is, the bigger the magnitude of that gradient is, which means the bigger the magnitude of your heat flow is. So heat's going to be flowing faster from up here than it is from down here. And then certainly here, where y equals 0, there's just no heat flow. And we'd see similarly, heat's flowing higher magnitudes the further you are away from y equals 0, and then smaller magnitudes here. So if we were to put vectors all over this thing, you'd see the further out you go this way, the bigger the magnitude is going the other way, and ultimately you'd have just no heat flow at the center because of that symmetry. But you could do the same thing here. There's no slope here. There's no driving force for heat transfer here at the origin, so there's no heat flow here, but you'd certainly get heat flowing downhill in each of these directions. So this is a one-dimensional system. We only have to worry about y. It makes the analysis much easier if we can assume that our system is one-dimensional. Okay, here's another one. So this time we have no y component. The temperature is not varying in the y direction, but only in the x direction. So how is it varying? Well, we look at our system. We do have a gradient, so dt dx is equal to 5. We would just differentiate this term with respect to x, and we get 5. So notice, unlike the other example problems, this is just a constant, which has some interesting heat transfer implications, and we've already covered some of them when we talked about the plane wall. So going back, if we looked at what's our dt dy, well, that's just 0. There's no variance in temperature in the y direction, and there's none in the z direction, which would be in and out of the screen. So we just get this derivative of dt dx equals 5. And if we were to plot this in just plotting the one dimension, we'd see temperature doing something like this. So just this constant slope, linearly increasing temperature from left to right. So how is heat flowing in this system? Let's look at a point on here. Let's look at just x equals 4. And again, we could pick a y, but as we learned in that last example, it's really not going to matter. It's going to be the same because there's no temperature variation in the y direction. So at x equals 4, what is the heat flux in the x direction? Well, we apply Fourier's law, which tells us that this equals minus k times dt dx, and I drop the partial derivative signs because there's only one variable here. So we can just use normal derivative signs instead of the partial derivative signs. So we end up with a flux, again, if we're considering that our k is just equal to 1, we end up with a flux of minus 5 watts per meter squared. So again, the directionality here is extremely important. So what does this directionality tell us? We have a negative sign here. So our gradient, our derivative itself was positive, meaning that temperature is increasing along with our coordinate system. When x increases, then temperature also increases at this particular point, and actually everywhere throughout this because it's just linear. So Fourier's law tells us that heat flows downhill. It flows against the temperature derivative, or against the temperature gradient. So our heat is flowing in the opposite direction. So our heat is flowing this way. And actually, one of the implications of this being constant, it means that heat is going to be flowing at a constant rate with respect to x all the way through here. So, and our flow is negative, which means our heat is flowing against our coordinate system. So if x is pointing this way, our heat is going this way, which just means that heat's flowing opposite to our coordinate system. So it kind of depends on how you set up your coordinate system. If we set it up differently, we could have a positive number there. So it's really important to just carefully and meticulously think through what is your system, where is the origin, and just make sure that you grasp, however you set it up, and whichever direction heat is flowing, make sure that you grasp how heat is traveling through your medium. So because of that, that linearly increasing temperature, our flux is going to be constant. And if here's our origin, we have this constant flux of minus 5 here. And that, again, that negative flux just means the heat is flowing against our coordinate system. So those are some simple problems. The next video will be building on this, and we'll just be looking at radial systems. But this is a pretty important implication that we'll get to later when we talk about thermal resistance. So if heat, and when we talk about the plane wall system, if the system is at steady state and there's no generation happening and there's a constant thermal conductivity, this will basically be the temperature profile you get, just linearly increasing temperature with respect to x, which means the heat flux through it is constant, and that will have some important mathematical and heat transfer implications.